Hello and welcome back to PC Retro Tech. At the end of the previous video, I left you with a bit of a puzzler. We'd been studying the history of this machine, the IBM 5150, the first IBM PC, and at the end of the video I revealed that I'd been working for months on a secret CGA graphics effect for the PC for the 40th anniversary, which I called IBM Project Chess. But I didn't reveal how it worked. I said at the end of the video that I didn't use any of the standard text or graphics modes of the IBM PC to do this effect. This is the effect that I'm talking about, and keeping with the theme of IBM Project Chess, the secret code name that they used when they were designing the IBM PC, it's an infinite chessboard scrolling towards you, and not only that, but also moving side to side. So in this video, what I want to do is explain exactly how I did this without using any of the standard text or graphics modes of the IBM PC. But I also want to explain how I got it to almost 60 frames per second on original hardware. You can see I didn't quite get there. There's a little bit of a mess at the bottom of the image. And that's something that I hope to actually fix as well in this video. With CGA graphics, there were only a handful of CGA graphics modes to choose from. You probably remember the 320 by 200 4-color mode that was used in a lot of games back in the day. You remember it had cyan, magenta and white plus a background color, or you could have green, red and yellow plus a background color. They were available in mode 4, and in mode 5 there was actually an undocumented palette, cyan, red and white, but that was basically it, and some low intensity versions of those. And then there was the 640 by 200 2-color mode, and this had just black plus one other color, but it was at a higher resolution. And I haven't included it here because you don't get this on a genuine CGA monitor, but if you have a composite monitor, you could plug it into the composite output and get a 160 by 200 mode with 16 colors, or with a bunch of tricks you could actually get many more colors. And the other option was to hack up a text mode. So there was the 80 by 25 or the 40 by 25 text mode, and if you change the character height to just 2 scan lines, and then basically chose a very specific character which was half in the background color and half in the foreground color, you could effectively get a 160 by 100 or an 80 by 100 graphics mode. So this was with snow in the case of the 80 by 25 mode on original hardware, but later clone CGA cards didn't have that limitation. The 40 by 25 mode doesn't have any snow, so there was no problem there. But that's what you were limited to just with the official modes and a few tweaks. For my little demo effect, I wanted to do something really unique for the 40th anniversary of the IBM PC. And so I decided to use something that Reenigne had announced, which he discovered something like 10 years ago, the so-called Improper Modes. And there's a link in the description if you want to see his blog where he announced this. So there are basically 2 kinds of improper modes. The first is what can only be described as a masked text mode. So basically, it's just like the ordinary 80 by 25 or 40 by 25 text mode, and of course you can set the character height to 1 or 2 or whatever you want. But this has one additional weird feature. So basically, the information that's in video memory not only encodes which characters are going to be displayed on the screen, but it also acts as a mask, a bit mask, for the pixels that are displayed. So basically you'd have your ordinary characters, and then bytes of video RAM are used as a bit mask which is logically ANDed with the pixels on the screen, so some of them get blacked out. And now it's a little bit more complicated than that even, but I'm going to give a few examples in a moment because this is actually the mode that I decided to use for my little effect. Now the other improper mode is basically just a 640 by 200 graphics mode, and you can select either 2 or 4 colors, and the 4-color one is really interesting because that's not standard at all. And I actually did a video on this on the sister channel PC Retro Programmer, where I actually found a CGA graphics card where this mode works perfectly, just like a normal graphics mode. But on original hardware, what happens is that only 3 out of every 4 bytes from video memory are actually displayed on the screen, and 1 of the bytes actually gets repeated. So you have some missing information and you have some repeated information. So that's, again, a really highly convoluted mode, and there's more complications which I haven't described here. For example, in the 2-color mode, you only get the even bits of data actually being displayed on the screen. So it's really messed up. But anyway, the first mode is the one that I decided to use for my little chess effect. In order to explain how this masked text mode works, let's just start with the ordinary 80 by 25 text mode. So instead of using a character height of 8 pixels, we'll just use 1 pixel high characters. So only the very top scan line of characters are going to be shown. And normally the characters are 8 pixels wide, so these first 8 here would be the top line of a character. And we usually pick character DE in hexadecimal. So this one codes for a character that has the first half in the background color and the second half in the foreground color. So in video memory, what you have is a character code. This is just the ASCII code of the character, which is DE in this case, followed by an attribute byte. And the attribute byte gives you the colors. So in this case, I chose green, which is color 2 for the background color, and color C, which is red, for the foreground color. And then for the next character, I again use character DE, the half character, and then color 1 for the background and color 5 for the foreground. And so you can see that you end up with 4 pixels that you can set the color of independently in each half of a character. Now, as I mentioned, in the masked improper mode, there's actually a bit mask that gets applied to the pixels that are displayed on the screen. So some of the pixels will actually end up being blacked out. And this is actually done 4 pixels at a time. So basically each byte of video memory not only encodes for a character or an attribute, but it also encodes for a bit mask that gets applied to the pixels. Now you might wonder how a byte, which has 8 bits in it, can possibly be a mask for 4 pixels rather than 8. But it turns out in the 80 by 25 high resolution improper mode, only every second bit gets considered. So if we look at this DE character byte here, every second bit would give us 1, 1, 1, 0. And if you look at the image, 1, 1, 1, 0, only the pixels that correspond to a 1 are shown, and the ones that correspond to a 0 are blacked out. So that's how it works, and in the second character the same thing's going to happen. We've got DE for the character code again, so the first half of this character will be 1, 1, 1, 0, and that 4th pixel will be blacked out again. Now you might imagine that the second half of each character is also encoded by the bytes that are in between here. That's almost true, but actually what happens is this 2C here doesn't correspond to the 4 bits at the end of this character, but it actually corresponds to the mask for the next character over. So it'll be the last 4 bits of that character. So everything's shifted along 1 for these alternate bytes. So let's take a look at 2C. It's 0, 0, 1, 0, and if you look at the image, 0, 0, 1, 0. So that pattern gets repeated all the way across the screen, but obviously on the very first character, these 4 bits here don't have a preceding character attribute to code for the mask for these. And so these 4 pixels actually end up just being completely black. Now that means that you end up with a black line running down the very left-hand side of your image, which doesn't look very nice. So what you can actually do is just black out this entire character and just make these all black as well, just by making this character a 0 character. And that way this doesn't display at all, and so your image just starts at here on the second character on the line. And so that cleans things up a little bit. So I got to thinking, why not use a different character other than the normal half character DE? So I went through every character in the character set to see what result it would have, and I eventually realized that if I pick a character like 3, the bit mask is going to be 0, 1, 0, 1, which means that every second pixel will be blacked out and every other pixel will be shown. And the pixels are so small in this mode, it's actually 640 pixels across the screen, that you really can't see them individually, so it just looks like a slightly darker version of whatever color it is. So of course, if you want to continue this pattern of dark light all the way across, then the attribute bytes also need to have that mask. So they have to have 0, 1, 0 and 1 in those alternate bits. But that leaves us with 4 other bits to play with, and there are actually then 4 different colors that you can set. You can set 1, 3, 9 or 11 as the colors, and they correspond to dark blue, dark cyan, light blue and light cyan. So when I realized this, that you could actually get 4 different bluish colors, I actually originally thought of calling my effect Deep Blue, which also has an IBM chess theme to it. So in the end I chose IBM Project Chess because this was the name of the official IBM project for building the IBM PC. At any rate, this means that what we can do now is have 2 pixels at a time with a color and all of the alternate pixels in black, and so everything's completely regular. We just set up character 3 all the way through video RAM, and of course we blank out the first character on the line, which we don't want to see anyway since it's defective, and then from then on all we have to do is set attribute bytes, and we can just set colors 1, 3, 9 or 11 as we wish. And so this gives us a high resolution graphics mode effectively with 4 blue colors. Now it turns out there are other characters you can choose. There's one that has the other bit pattern with 1, 0, 1, 0, so that the other pixels are shown, and then you get 4 different colors, but I'll leave it to you to figure out what those actually are. So at any rate, these are the 4 that I wanted to choose for my graphics effect. Well, it turns out there's still a number of problems that I had to solve in order to get this effect to work. The first is that with 80 characters across the screen and 200 scan lines down, with each character having an attribute byte and a character byte, you end up needing twice as much video RAM as the CGA card actually has. So in the end I had to settle for a window in the middle of the screen, and this is actually only 64 characters across and 128 scan lines down. And so this ends up taking up all of video RAM. Now you lose 1 character on the left hand side due to that defect that I talked about, so you end up blacking out 1 character, and so you really only end up with 63 characters across. But this gives you a resolution of 126 by 128, and I think it doesn't look too bad. So the second problem that you have is that there isn't anywhere near enough time to update all the pixels on the screen every frame. In fact, you don't even have enough time to update all the pixels just in the chessboard region, not anywhere near enough. So what you have to do is just update the pixels that are actually changing color each frame. So this is pretty complex. So there's the movement towards you of the chessboard. Now obviously the only thing that changes color there is the horizontal lines between the squares going down the screen. So those can just be copied from somewhere else in main memory, since it's just consecutive memory across those scan lines that needs to be copied over. But for the side-to-side movement, things are much more complicated. You've got these perspective lines which are really a little bit tricky to draw in the first place, let alone to copy into video RAM. And these really only need to update a handful of bytes per scan line, but for every scan line in the image. So what I actually do is have a pre-computation period before the effect starts, where it actually writes some code out in an automated way into memory that's actually going to run for each scan line that will just change the colors of the pixels that are changing between each frame of the effect. So that leads us to the third problem that we have, and that is the amount of memory this effect takes up. So obviously you have to have multiple copies of the image in memory in which you can take the scan lines from for the horizontal lines that need updating. And so there's really a lot of copies of the image needed for that. And then you need code space for all of the code that gets written out for updating the perspective lines. And so altogether, this takes up essentially all of the memory in the IBM PC, all 640 kilobytes. So then we come to the fourth problem with this effect, and that has to do with the improper mode being based on the 80 by 25 text mode. And unfortunately, this mode has snow. So basically, if you try to update video RAM whilst the CGA card is reading the video RAM in order to display pixels on the screen, then you'll get snow on the screen, and it really looks ugly. So what you have to do is only update video RAM when the CGA card's not reading from video RAM. In other words, when it's not outputting pixels. So there's two different regions where you can do this. At the end of a scan line where it's been displaying pixels, when it goes blank before the next scan line starts, there's a little portion at the right of the screen and the left of the screen for each scan line. This period can be used for updating the video memory. And so I actually do all of the updates that are required for the forward movement of the chessboard in those horizontal blank periods. And then there's the big block of time at the bottom of the screen and the top of the screen where it's black. And that vertical blank area I use for doing the side-to-side movements. And so this turns out to be really quite complicated to do in total, because you first of all have to detect the end of a scan line when it finishes outputting pixel data, and then you have a very precise and very short period of time to do all of your updates to video memory for whatever pixels you try to change. And this really was quite a lot of work to compress everything down using assembly language in such a way that it would fit into those regions. And as you can see, at the end of the day, I didn't quite get the whole effect to work the way I wanted. At the bottom of the image, there's this wiggle where I'm not actually getting all of the scan lines updated. So basically, it does actually do all of the vertical movement updates in that region, but it doesn't do the horizontal side-to-side updates, and so you don't end up with squares but weird stripes with wiggles in them. So what I'm going to try and do now is find a way to squeeze even more out of this effect so that I can get everything into 60 frames per second. Now the first thing I'm going to try is replacing some of the C code, and of course all of the effect code is in assembly except for one loop down the bottom here which actually controls which frame is displayed. Now I know it's a long shot, but the C compiler is so bad it's actually worth trying to put this in assembly. Well, it took me almost half a day to write the assembly language just to get rid of that big C loop that I was talking about. But I seem to mostly have it working now, and we're actually 3 scan lines closer to the bottom of the screen every frame now. There's a little bit of snow on the left-hand side, as you can see, but I think that should be easy to get rid of. So now I'm having another idea for speeding things up, and this relates to the overhead of the side-to-side movement. The way that works is that each scanline that needs to be updated, there's a little routine for it that's pre-compiled into memory by the pre-computation that happens before the effect runs. And the problem with that is every time you want to update a scanline, you've got to compute the address of the relevant routine in memory, then call it using a far call, and once it's done it has to return using a far return. And all of this adds a whole load of extra overhead. It could be 20 or 30% overhead just for that stuff. So what I'm going to do is chain some of these scanline update routines together. So basically all of the scanlines that need updating in a horizontal stripe of the chessboard are going to be chained together so that they don't actually have to do a far return and a far call in between them. So there'll be one far call and one far return for each horizontal stripe instead of each horizontal scanline. And that should save a fair bit of the overhead that I've currently got. But the problem is then I start to run out of memory. I need some extra code for each of these update routines to do the chaining, and it turns out that I am just 1 byte short for each of those update routines. Anyway, I figured out that I can actually juggle things around, and if I sacrifice the very final scanline of the image entirely, then I can actually just fit everything in memory, just. So I'm going to give it a go and see if I can make it work, because if I can, then we should be able to push out a few more scanlines. Well, an entire day has passed, which means this video won't be coming out on the weekend. But as you can see, I've actually been successful with this idea. Amazingly, we're only stopping 3 scanlines before the bottom of the screen now, and I'm not doing that for performance reasons at all. In fact, it's just because I'm out of memory. So the performance of this is way better than I anticipated. I don't really understand why that trick saves so much time, but I'll take it. So there is still a small glitch left. You can see that when the image moves to the leftmost extent, there's a little glitch around some of the squares, and that is something that can probably be fixed at a later date. I'm not going to bother about it now because it's not very distracting, and this video has taken long enough to produce. So what I'm going to do now is sacrifice the final scanline, and hopefully that will free up enough memory to allow me to compute the remaining scanlines for the horizontal movement, and then we can have the chessboard going all the way down without a kind of weird defect at the bottom. Of course I'll have to move everything down 1 scanline as well. I don't want to leave just a blank scanline at the bottom of the image. But all of that should be relatively straightforward to do from here, and so through the magic of television you should shortly see the final working effect. And there it is, it's working at last. I'm pretty happy with the way it turned out. I did have to sacrifice a couple of scanlines in the end instead of 1, again down to memory usage rather than performance. But this is the first effect that I've personally done in CGA that run on an original IBM PC at 4.77 MHz at 60 frames per second. So I'm pretty happy with that, and I think we can call this a true demo effect. So there are a few little things that I'd like to improve. One is obviously that little glitch that I talked about, but also the pre-computation time is very slow at the moment. It takes about 30 seconds, and I think I could probably get that down to about half if I really put the effort in. It'd also be nice to get the performance of the effect itself up just slightly so that I could turn interrupts back on. At the moment they're off, and so I can't use those to detect a key press to end the demo, so it just runs forever at the moment. And obviously, it'd be nice to have interrupts for music or something like that as well. And of course it'd be great to get the memory usage down. I don't really see a way of doing that at the moment, but it is using up all the memory on the machine, and it probably wouldn't even run on machines that have lots of drivers installed, or maybe even different DOS versions. So that would be one thing that would be really worth fixing. But there are also some improvements that can be made. For example, I could put some images at the top of the screen where that sky is, And these could even change during the demo. So when the chessboard reaches its maximum extent side to side, there's a little bit of time momentarily where it's just moving forward and not side to side anymore. And in that time, you can actually do some work. For example, change the images at the top of the screen. So that would be worth doing. And the other thing that would be really good to improve is the very regular side-to-side movement. It isn't really restricted at all at the moment, even though a lot is pre-computed. We're not pre-computing frames of the final product here. The pre-computation is just because we don't have enough time to update all of the pixels in that region. In fact, you can have any side-to-side movement, or back and forth movement for that matter, that you want. And I just didn't get around to writing a driver that does something more interesting, like moves much further, or changes speed, or does something less regular, so it doesn't look like it's just on a repeat. So lots of things to be improved there, and one day I'll get around to it. But as you probably guessed, this week I've run out of time completely, and so that's it for this week. If you like this sort of thing, don't forget to subscribe to the channel and give a like on the video if you enjoyed it, and we'll see you in a later video. Bye.